Okay, I think we can get started. Let me actually do this. I don't know how to do that. Okay, I think we can get started. Okay, that's better. Yeah, it's better to be lecturing from Hawaii, right, than my office. Although I might use the whiteboard in the lectures coming up. Okay, now we're in lecture 13 of Digital Design and Computer Architecture. And we're going to start having even more fun because finally we're going to start improving performance significantly today by the use of the concept of pipelining. And we're going to do that more and more in the coming weeks. And this is such a fundamental concept that it's employed essentially in all processors today, even in low performance processors, I should say. None of the processors that I know of today are really multi-cycle, and certainly not single cycle due to the huge contrivedness problems of single cycle that we discussed last time. Okay, so this is what we're going to do. Today, we're going to start pipelining. We'll start some pipelining issues, and there are a lot of interesting issues that we come up with pipelining because we're going to process multiple instructions in parallel concurrently at the same time. And we're going to continue those issues next week, data dependencies, control dependencies. And then we will start improving performance even more by executing instructions out of order. Out of the program order. We're not going to do that in pipelining, at least initially. And then we'll talk about out-of-order execution concepts and some really interesting issues like branch prediction the week after that. So these are your readings for this week and next week, but I'm going to supplement it next week again. And this is our agenda. We've already covered single cycle and multi-cycle microarchitectures, analyze their trade-offs. We're going to do that even more. And I've already said this. And next week and the week after, we're going to actually get closer to the state of the art in general purpose microprocessor design, which is going to be even more fun, if you will. Okay, so let's jump into the lecture. This is just to jog your memory. Remember that this was a single cycle MIPS processor that we had last time, at least from your book. And this is the single cycle MIPS finite state machine. And the question is, can we do better than this? We asked this question. And we found out issues with single cycle designs, which I'm not going to go through again, but you can watch the last lecture, lecture 12 for it. And the big issue was basically the worst case instruction determined the clock cycle time, but there were also other issues. So we decided that a multi-cycle processor where you process instructions across multiple cycles is a better idea overall. And this is the multi-cycle processor we designed. And this is a multi-cycle processor's finite state machine, which is much more complicated than the single cycle finite state machine that I showed you just a couple of slides ago, which is this one. So by complicating the control logic and sequencing through states such that we can process each instruction in different cycles, we can come up with a much better design to process instructions. So single cycle and multi-cycle processors both strictly obey the von Neumann model at the microarchitecture level. They process one instruction at a time. After the finishing of one instruction, they move to the next instruction. So it's clear for single cycle, but for multi-cycle, as you can see, for example, if you process a load word instruction, you sequence through these states. And then after you finish load word, you go to the fetch state again. And then you execute, for example, process an R-type instruction, for example, in the sequential order. So you never violate the von Neumann's sequential processing principle at the microarchitecture level. Today, we're going to violate that at the microarchitecture level, but at the architecture level, we're not going to expose that violation to the architecture. Our goal is to improve performance. Our goal is not to break the contract between the hardware and the software. Okay, so we also asked the question, what is the shortcoming of this design? And we actually discussed that. Basically, only one instruction, only a small fraction of the resources of the pipeline are being used at a given time. For example, when you're fetching the load word instruction, you're using this part of the pipeline, whereas nothing is happening on the, not pipeline, the processor. Nothing is happening on the other parts of the processor, right? And we're going to try to fix that today. And we also asked that, what does this design assume about memory? It assumes basically the memory is one cycle in this particular finite state machine. But at the end of last lecture, we discussed how this sort of multi-cycle microarchitecture can easily accommodate multi-cycle memory as well. So if the memory takes 100 cycles to access, you can stay in the memory access state. You can add a special memory access state inside this finite state machine, and you can let the machine stay in that state for 100 cycles before you move to the next state. And the memory can tell you when the data is ready. And the memory is ready bit that indicates whether or not the data is ready can be the transition trigger to the next state. Clearly, we know how to design finite state machines by now, and you can use a ready bit coming from memory to indicate when you should transition to the next state, right? And if you're really interested in knowing more about this, I mentioned that you should watch some other lectures that I pointed to last time, or read the backup slides that I gave you last time, or read your book, which has more detail. Actually, the book in this case is the Pat and Patel book, which covers multi-cycle memory access. So in this particular lecture, we're still going to assume memory is single cycle in a pipeline processor. Keep that in mind. We're going to change that later on, but you will also see that a pipeline processor can easily handle multi-cycle memory by stalling or by waiting for memory. And we will see that. We will see in pipeline control. But pipeline works best when you have single cycle memory. Okay, but let's talk about the shortcoming of this design again. So basically, we're going to ask this question: can we do better than these multi-cycle microarchitectures? And the answer would be yes. And we've already discussed this, but what limitations do you see with the multi-cycle design? And I think I'm going to answer it. And the answer is limited concurrency, which I just told you earlier as well. Basically, you have a lot of hardware resources, and you're using only a fraction of it at a given clock cycle. Some hardware resources, in fact, most of the machine is idle during different phases of the instruction processing cycle. Basically, fetch logic is idle when an instruction is being decoded or executed, or writing its result back to memory, or back, either memory or register. And most of the data path is idle when a memory access is happening, basically. ALU is idle, fetch logic is idle, and write back logic is idle, register file is idle, decode logic is idle. You're just doing memory access for that particular instruction that you have, that you happen to have in that stage. And clearly this leads to a lack, I shouldn't say loss of performance necessarily, but lack of potential performance improvement. We're not really utilizing the hardware in the best way to maximize performance. And people have realized that and basically asked the question, can we use this idle hardware to improve concurrency? That hardware has to be there. Why does it have to be there? Because there are instructions that need that hardware at some point in time. Maybe not in this clock cycle, but they're going to need it in 5 clock cycles later. Whenever that instruction reaches the stage where it needs the hardware, that hardware is needed, right? It's necessary. So why not use it for other purposes as well? Why not improve concurrency? And that's the idea. So what's the benefit of more concurrency then? It leads to a higher instruction throughput, meaning you can process more instructions concurrently at the same time. You can complete more work in one cycle, and you can finish your program faster, right? Remember the performance equation? It said we have a number of instructions, and we have cycles per instruction, and we have clock cycle time. If we can reduce the cycles per instruction, or in other words, increase the instructions per cycle, these are inverses of each other clearly, then we can reduce the execution time of a program. Of course, while we're doing that, we should be careful that we do not increase the clock cycle time significantly, right? We want to reduce the cycles per instruction or instructions per improve instructions per cycle, but we should not increase clock cycle time significantly. And that's the idea of improving concurrency in general. So basically, the idea of pipelining to improve concurrency is when an instruction is using some of its resources, some hardware resources in its processing phase, process other instructions on idle resources that are not needed by that instruction, and apply this consecutively to consecutive instructions, essentially. That's the idea, to maximize the concurrency you have in the system. So basically, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode the next instruction and fetch the instruction after that. When an instruction is accessing data memory, execute the next instruction, decode the instruction after that, and fetch the instruction after that in program order. And when an instruction is writing its result into the register file, access data memory for the next instruction, and basically ... everything I said applies basically. So while you're doing something for instruction X, do the previous thing for instruction X+1, the next sequential instruction, and do the previous thing for instruction x plus 2 and x plus 3, x plus 4, x plus 5, ... as long as you can pipeline the processing of the instruction. And this is a very powerful idea, and we're going to make it work, essentially. And that's basically the key idea of pipelining. The rest is, how do you make it work? Okay, so basically the idea is we can have instructions in different stages. And remember, these are different stages. This is the instruction processing cycle, let's say. It consists of 6 stages, but we reduce it later to 5 stages, kind of. But again, there's nothing fundamental about 5 or 6. You can make it 20 if you want, with the idea that we're going to see. But we're going to see a simple 5-stage pipeline in this case. Remember, this is our multi-cycle processor. Our multi-cycle processor already has these latches or registers, right? And they were there for a different purpose. The purpose was really to execute one instruction in different clock cycles. But basically, we're going to stretch the idea a little bit and say, while we're executing this while this blue instruction is in this clock cycle, meaning writing its result to the register file, for example, I'm going to have a yellow instruction doing an ALU operation. And at the same time, I'm going to have a green instruction being decoded and accessing the register file. And at the same time, I'm going to have a red instruction being fetched at the same time. This way, in this cooked up example, I have 4 instructions that are being processed in the same cycle at different stages. And hopefully I can finish one instruction every cycle this way, as opposed to doing one instruction every n number of cycles, where n is dictated by the instruction, how many cycles it takes to execute the instruction. Of course, this is a pictorial example, and this is just to motivate you. This is not real. We want to be much more careful than this, because if you actually divide things like this, you'll run into issues. You cannot just take a multi-cycle processor, because you designed the multi-cycle processor. We have a beautiful multi-cycle processor in our last lecture. Can we just take it and chop it up like this? I showed you, and the answer is no. You cannot chop it up like this, because look at this. What's happening here is we have a single instruction and data memory. And remember, we wanted that for a multi-cycle. Now, what happens if you want to fetch an instruction at the same time another load instruction is accessing that data memory? Well, you have a problem, right? So we designed the multi-cycle processor to actually minimize their hardware resources, but pipelining goes against that a little bit. We need to actually, if we really want to do multiple instructions concurrently, we actually are going to need to replicate some of those resources back. So a pipeline processor is not really just multi-cycle processor taken into the next level. It's really about how do we design a processor to process multiple instructions consecutively in consecutive cycles. And we will see that. That's why this picture, even though conceptually it's very nice, you should not take it as an implementation of a pipeline processor, because implementation does not go from multi-cycle to, okay, I designed the multi-cycle, now chop it up. No, it doesn't work that way. You really need to design the pipeline processor from scratch, if you will. In fact, the single cycle processor is easier place to start and pipeline the processor. And we will see that. I will do that actually in this lecture. Okay, so we're going to talk about pipelining basically. I've given you the basic idea and basic insights. I will repeat it again in a different way. So more systematically, the idea is to pipeline the execution of multiple instructions. And pipelining is not a foreign concept to human beings. It's been around for a really long time. So for example, in factories, we have assembly line processing of instructions, right? In a car factory, there are people who are specialized to do things. Well, robots nowadays are specialized to do things. So for example, one part of the factory is specialized for mounting the engine at the right place. Another part of the factory is specialized for mounting the tires. Another part of the factory is specialized for mounting the top level body. And this happens in a pipeline, right? You don't produce, you don't take one car and wait until the production of a single car so that you start the production of the next car, right? That's actually a huge waste of time. Each car goes through the pipeline, and while one car's engine is being mounted, another car's tires are being mounted, and another car's body is being mounted, and who knows what else, right? This could be a very long pipeline. And that's the same idea, essentially, in this case. Now, car pipeline is much nicer, I think, because there are no dependencies between different cars, right? When you actually are processing one car and creating one car, the next car has really nothing to do with this car, right? There's nothing you need from the previous car to really assemble the second car. That's true for the third car, fourth car, fifth car. So this is really a good pipeline and perfect or ideal pipeline, as we will see, because consecutive cars that you need to assemble have nothing to do with each other in a sense. They don't depend on the prior cars that you processed. Now, that's not going to be true in an instruction pipeline. Instruction pipeline is going to be more difficult to handle. And that's the difference. That's why this is also exciting and interesting. It's not as easy, I should say, as pipelining the processing of pipelining the assembly of a bunch of cars. Okay, so but that's a very good analogy to begin with, basically. So the idea, we're going to, similar to a car assembly factory, we're going to divide the instruction processing cycle into distinct stages of processing. Okay, and ensure there are enough hardware resources to process one instruction in each stage. And this is going to be really important. We should not miss any hardware resources for a given stage. And that's what I meant by instruction and instruction fetch and data access. You need memories for both. That's why we're going to replicate the memory or add more ports to the memory. In each stage, we're going to process a different instruction. And instructions consecutive in program order are going to be processed in consecutive stages. And this makes sense because at the higher level, we have a sequential programming model, which is the von Neumann model. At the higher level, we're not going to break that. But internally, we're going to break that. Internally, in the microarchitecture level, we're going to fetch an instruction before the prior instruction is complete. But we're not going to report the results to the software. Okay, so the key benefit, and this is the major benefit of pipelining, is it increases instruction processing throughput. Why? Because basically, you're really processing more instructions in a given cycle. Basically, you're really improving instructions per cycle, right? IPC. That's the inverse of CPI. So for a given instruction, maybe you're not changing the cycles per instruction. We're going to talk about that also in a little bit. But when you take together multiple instructions at the same time, you're really trying to finish one instruction per cycle. Right? Every cycle, you put one instruction into the pipeline, and every cycle, you get one instruction out of the pipeline. So ideally, your instructions per cycle should be one. And on average, your cycles per instruction, because of that, should be one as well. So from a throughput perspective, your throughput should be, I'm finishing one instructions per cycle. That's ideal. Now, latency is a different issue. Latency of an instruction will remain the same, essentially. In fact, it will increase, as we will see, because of the overhead of pipelining. But this is the difference between latency and throughput, as we will see again. Okay, and keep that in mind. Latency and throughput are usually against each other, and we're going to see that. And never confuse latency and throughput with each other. And pipelining is a great place to understand the differences between latency and throughput. Throughput is also called bandwidth sometimes, and I'm going to define it as bandwidth in a little bit as well. So the downside, start thinking about this basically. The downside, we'll add more hardware, essentially. We need certainly registers to store the intermediate results from each stage, as we have done with multi-cycle, but we're going to do even more. We need other hardware. We need to replicate some hardware so that different instructions, different stages can access memory at the same time, for example, or the register file at the same time, or do different operations at the same time. So that it's going to cost more hardware than multi-cycle for sure. And we will also need to pay some sequencing overhead so that the instructions actually go through the pipeline stages and latch their results into the registers. And all of this will be coming. But before we get into the downsides, let's see the upsides with an ideal picture, let's say. So let's take a look at this picture. Let's assume that we have 4 independent add instructions. They have no dependencies with each other. The second one doesn't require the result of the first one, and none of them require the results of any of these instructions that are being processed. If you have a multi-cycle machine, assume that an add instruction goes to fetch, decode, and execute and write back 4 cycles. Basically, a multi-cycle machine spends 4 cycles per instruction, right? And you can see that it finishes the instructions after 16 cycles. A pipeline machine, if there are no dependencies, and if you design the pipeline nicely, while you're decoding the first instruction, you fetch the second instruction. While you're executing the first instruction, you decode the second instruction, and you fetch the next instruction. And while you're writing back the result of the first instruction, you execute the second instruction, and you decode the third instruction, and you fetch the fourth instruction. So basically, in the steady state, you have 4 instructions being processed in a cycle. Steady state is basically when you fill the pipeline. So you can see that all of the pipeline stages are full in cycle 4 over here, as you can see. And assuming that you keep adding more independent add instructions to your pipeline, you keep the pipeline full, right? So keep this in mind. But basically, what's happening here is in the steady state, if you keep the pipeline full with adds, you are finishing four instructions per 4 cycles, as you can see, meaning 1 instruction per cycle, as I mentioned to you, right? If you look at this over here, once the pipeline is full, you're finishing the first instruction in 1 cycle, next instruction in the next cycle, next instruction in the next cycle, next instruction in the next cycle, and ... basically. So in the steady state, our throughput is 1 instruction completed per cycle, which is much faster than or higher throughput than 4 cycles per instruction, or 1 instruction finished every 4 cycles, right? Okay, so of course, this is beautiful and nice. The problem is life is not always this beautiful, meaning you don't always have independent ads. And the problem happens when the second ad, for example, is dependent on the first ad. It requires a result of the first ad. How do you keep the pipeline full? And we're going to see a lot of issues like this in the pipeline and ensure that the pipeline is full and working as much as possible. And that's going to be the difference from assembly line processing of cars, for example. In cars, you don't have this problem. In instructions, unfortunately, different instructions may be dependent on each other because the program as a whole is trying to accomplish something, right? Whereas in a car factory, there's no dependence between the cars. Of course, the cars, the factory as a whole is trying to accomplish something, but it's really not a single program. It's really trying to maximize the production of many different cars, which have nothing to do with each other in a sense, except they're using the same resources to be assembled. Okay, so basically life is not always this beautiful, and we're going to look at why life is not that beautiful, and we're going to solve a lot of problems with pipeline. But before I get into it, let me also give you another analogy in laundry. I assume some people here have done laundry. I do laundry. I was doing laundry when I was a college student as well. And laundry analogy, this is taken from one of the books, Patterson and Hennessy book, actually. Basically, if you don't pipeline the processing of laundry, you will be up for a long time. That's the key idea over here. So if you look over here, the laundry consists of placing a dirty load of clothes in the washer. When the washer is finished, you place the wet load in the dryer. And there's a dependency between the washer and dryer, clearly. So it's similar to an instruction. You fetch the instruction, and then you have to fetch the instruction before you can decode it, right? That's why the laundry analogy is kind of nice over here. And then when the dryer is finished, take out the dry load and fold. And when the folding is finished, put the clothes away basically somehow, or ask your roommate to do it for you, whatever you would like to do. And assuming each state takes 30 minutes over here, this is a multi-cycle laundry machine, let's say. Basically, you finish one load every 4 cycles, and each cycle is 30 minutes in this case, as you can see. So one load finishes after 2 hours, and then you start the next load after 2 hours. That takes 2 hours, and then you start the next load. So basically, finishing 4 loads takes 8 hours. And essentially, if you start at 6 p.m., you're up until 2 a.m. That sounds terrible, right? And that's, if you have 4 loads, this is not the way to do things. So, but let's analyze this. Basically, steps to do a single load are sequentially dependent. Basically, you have to fetch the load and put it into the washer. Only after that you can dry it. Only after that you can fold it. Only after that you can put it into the drawer, right? No dependence between different loads in this case. So this is more like cars in this case. There's no dependence between this load that you're processing and this load that you're processing. Instructions will be different. Different steps do not share resources. Clearly, there's no sharing. Washer and dryer are different, right? They don't share resources. So in that sense, it's nice. Folding does not share resources with dryer also. Okay. And finally, well, I guess that's all in this case. So basically, this is a good thing to pipeline. And once you pipeline it, it looks like the picture at the bottom, basically. So pipeline 4 loads of laundry in parallel, very similar to those 4 add instructions that I showed you, right? As opposed to taking 8 hours in total, basically we're done at 9:30 p.m. as opposed to staying up until 2 a.m. Why? Because now we can do 4 loads of laundry in parallel consecutively. We start consecutively. There's no need for additional resources in this particular case. Throughput has increased by 4. Why? We're basically finishing one load every 30 minutes, if you will. And latency per load is the same. So this is important. This is if you look at one single load, it's still taking 2 hours, right? It was taking 2 hours before. It's taking 2 hours again. Every single load takes 2 hours. But because you're concurrently processing the loads, overall, 4 loads takes much shorter, right? So latency of a single load or instruction is the same, but throughput of all instructions increases. Okay, keep that in mind. That's the key for pipeline. Okay, so let's take a look though. There may be some issues even with laundry. And I think this is going to become potential issues in our case as well. And we're going to solve these things in an instruction pipeline in a similar way. So in practice, unfortunately, the dryer is the culprit sometimes. And in my experience, dryers have always been the culprit for some reason. Somehow people are not good at creating cost-effective dryers that can dry things fast. And that's the reason, I think. Basically, dryer takes 1 hour in this case. As you can see, if the dryer takes 1 hour, your pipelining is not perfect anymore, right? You cannot start the second load. Well, you cannot start the second load's drying phase, let's say, I should say it that way, until the first load's drying phase completes. Okay, so dryer really makes everything, the throughput, it really reduces the throughput. It reduces latency, obviously, but it increases latency, obviously, but it also reduces throughput. Why? Because it's taking 1 hour as opposed to 30 minutes. So this pipeline stage is a bit annoying, right? So either you have it, how do you solve this problem? Now your throughput has decreased, clearly. You're finishing one load every 1 hour, as opposed to every, so if you go back, this is the nice thing where you're finishing one load every half an hour, right? Now we're finishing one load every 1 hour because our slow stage is the culprit. Well, how do you solve this problem? There are two solutions. Well, there are potentially more than two solutions, but I'll discuss two solutions. One is get a faster dryer. Clearly, faster dryer gets you back to this. So this may be, for example, an ALU. ALU is slow, or it could be memory access. It could be slow, right? Get a faster one. Okay, you cannot get a faster one because you've pushed the limits, right, of your combinational logic or the dryer design, or it's not cost effective to get it. What do you do then? Well, get two dryers, right? Basically, dryer A and dryer B. And basically, you're limited by resource dependence here. You need one dryer is taking too long. If that dryer is taking too long, start the drying of the second load on a second dryer called dryer B. And since there is no fundamental reason why you cannot start the second load, other than the fact that dependence on the dryer was limiting you before, this fixes the problem, right? So basically, you start alternate loads in alternate dryers. As a result, you restore the throughput. So by adding more hardware to the system, by adding more dryers to the system, we restore the throughput of the laundry to be one load every 30 minutes again, right? So as opposed to having two loads, now basically we have 2 loads per hour or one load every 30 minutes using 2 dryers, right? Now, hopefully this makes sense. We're going to see potentially similar issues in a pipeline. And this is called a resource dependence. We're going to cover it in more detail, or hardware dependence. Essentially, your pipeline throughput will be limited because different instructions at different processing, different instructions may need the same resource. And if your resource cannot be made faster for some reason, you replicate the resource. And that's a fine solution to the problem. Of course, it adds hardware costs, as you can see, right? So if you want, and this is the takeaway, basically. Pipelining can improve your throughput, provided that you can provide enough resources to solve issues that look like this. And this may look like a simple issue. It's absolutely a real issue in real systems, real dryers, in my opinion. I've actually faced this when I was a college student. Even right now, I'm facing it. Actually, dryer takes always longer. Those damn dryers. I don't know why they cannot be faster, but I know the physical limits. Assuming, given a cost point, you really cannot make the dryer faster. Of course, you can pay a lot more cost and make your dryer faster, but again, design point is a cost point, right? Potentially. So basically, this is a real issue, and we're going to solve real issues like this in pipelines also. And this is just one of the issues. This pipelining of laundry doesn't have some of the issues that we're going to see in instructions in a little bit, like the dependencies between different loads, for example. But resource dependencies, hardware dependencies, they exist, as you can see. Okay, so let's talk about an ideal pipeline. So our goal in pipelining is increased throughput with little increase, or as little increase as possible in cost. And cost is really hardware cost in case of instruction processing. There's also a latency cost, as we will see in a little bit. But hopefully you see the example of the hardware cost. So if you would like this to happen, you need to have an ideal pipeline. And we will see that instruction processing is not an ideal pipeline. But let's take a look at what an ideal pipeline should look like. So an ideal pipeline should repeat identical operations. Basically, what does this mean? The same operation is repeated on a large number of different inputs. So for example, in case of laundry, inputs are different loads. You have 4 loads of laundry to do. And operation are really dryer, washer, folding, and putting it into the wardrobe, right? So basically, the same operation is repeated on a large number of different inputs in case of laundry, because all laundry loads go through the same steps, right? If you think about instructions, we're going to see this later on. Even though this is mostly true, this is not perfectly true, right? And also, it depends on how you design the pipeline. Not all instructions go through the same processing steps, and we know that already, right? Even though they mostly go through the same processing steps, for example, an add instruction in MIPS ISA at least doesn't require a address calculation stage. It doesn't require a memory access stage, right? Meaning that you don't repeat identical operations perfectly in an instruction pipeline. And we're going to see that affects our throughput in a little bit. Okay, the next thing in an ideal pipeline is ideally we would like to repeat independent operations, completely independent. There should be no dependencies or dependencies between repeated operations. I actually like using the term, I don't know what happened, dependencies. Am I still sharing? Okay, I guess I'm not sharing. Thank you for saying that. Okay, what I did was I corrected this word dependencies to dependencies because I want to be consistent. Dependencies are a perfectly fine term, but I usually use dependence to indicate that one operation is dependent on the other. So basically, there is no dependence between repeated operations. So a laundry is a perfect example of this, right? Different laundry loads have nothing to do with each other. But instructions, unfortunately, that's not the case. And we will see that this is going to be a problem in our pipeline. In fact, this is going to be perhaps one of the most important problems in a pipeline. So, and then the last thing is uniformly partitionable sub-operations. So what does this mean? This is a fancy word. But basically what this means is that processing can be evenly divided into uniform latency sub-operations that do not share resources. So each stage of the pipeline is evenly divided and you're doing useful work for the entire stages of the pipeline. So in the laundry example, washing takes exactly 30 cycles. Drying takes exactly 30 cycles. Folding what you have dried takes exactly 30, I say cycles, 30 minutes, right? 30 minutes. And putting the stuff that you folded into the wardrobe takes exactly 30 minutes. Now, if any of these stages take different amount of time, it's not an ideal pipeline anymore. Why? Because you're wasting some amount of the time. Well, in real world, it's a clock cycle, right? Basically, for example, if your washing takes 15 minutes, but you're waiting for the entire 30 minutes, you wasted half of that pipeline stage or clock cycle. And we're going to see that this is real in instruction pipelines. Now, this may not be a problem in a laundry pipeline, but you need to be careful. Again, you need to balance the different stages of the pipeline nicely. Whenever you have a clocked system, synchronous system, where the pipeline stages take exactly the same amount of cycle time, you will have this sort of problem. And we will see this in a little bit. So basically, automobile assembly line or doing laundry are actually quite close to ideal pipelines. You may actually find some parts may not be perfectly ideal, but they're much more ideal compared to an instruction pipeline. And we will see the instruction pipeline in a little bit. Okay, what about the instruction processing cycle? And we will see. So, but let's take a look at this ideal pipelining a little bit more before we go into instruction processing cycle in a little bit more detail. So I'm going to examine this ideal pipeline, but again, from an instruction perspective, not necessarily a laundry perspective. So we're going to look at a computer terminology. So bandwidth means bandwidth, same as throughput in this context that I'm going to use it. So, okay, this is like a single cycle processor, right? We have a latch, a register over here, and another register. In a single cycle processor, it's the same. And we have some combinational logic that does fetch, decode, execute, memory access, and write back. Let's assume that it takes t picoseconds. The throughput of the system is 1 over t, right? Assume that this is a stage. Don't worry about a single cycle processor right now. Assume that this is a sequential stage, potentially part of a bigger pipeline. Now, ideal pipelining divides the stage into two so that you can increase the throughput, double the throughput. But while you're doing that, you need to make sure that the division is nice, such that each stage doesn't really lose any of the divided work. What does this mean? Whenever you divide this to t over 2 picoseconds and have combination logic over here, you'd better not increase the delay of the combination logic somewhat, because you need to perfectly be able to divide the combination logic, right? And that's usually not easy, actually. But assume that you've ideally divided. Ideally, you should have t over 2 picoseconds over here and t over 2 picoseconds over here, and your throughput becomes t2 divided by t. Nice. And you don't lose any latency, right? Because your total latency is still t picoseconds to execute, fetch, decode, execute, memory access, and write back. Now, you can clearly already see that this is a problem, right? This is not going to happen in an instruction pipeline, because even if this is t over 2 and t over 2, remember, we have sequencing overhead. So we're going to get back to that. So your throughput is not going to be 2 over t potentially. Even if it's 2 over t, your latency is going to increase, right? Okay. Now, again, ideally, you would like to be able to keep dividing the pipeline or a stage into any arbitrary number, t over 3, for example. Now, this is a 3-stage pipeline. So this is a single stage. This is 2 stages. This is 3 stages. And if you have an ideal pipeline with 3 stages, each stage should consume t over 3 picoseconds. And you should be able to nicely divide the processing cycle, as you can see, fetch, decode, execute memory access, and who knows what memory access write back. Now you can see issues appearing, right? Maybe you're not going to be able to perfectly do this because it's not perfectly divisible combinational logic that you're dealing with over here. But assume that you can do that, your throughput becomes 3x compared to the baseline, and your latency stays the same. But again, in a real instruction pipeline, what I just said cannot be true. Your latency cannot stay the same because we have latching overhead, right? We have the register overhead over here, which we call the sequencing overhead before. And you have the clock skew also. Everything we discussed in timing and verification lecture. Okay, so let's take a look at a more realistic pipeline. So let's take a look at throughput. So this is the non-pipeline version with delay t. It's t picoseconds, everything. The real bandwidth of the system is really 1 divided by t plus s, whereas s is the register delay, essentially. Sequencing overhead, in other words. So you have t combination logic delay plus s sequencing overhead. So what goes into the sequencing overhead? Remember timing and verification lecture 8. If you really want to really understand again, go back and watch lecture 8 right now. That's the register hold and setup times plus the clock skew, which affects the register hold and setup times, right? Okay, so it's not exactly 1 over t. So if s is really small, it's close to 1 over t. If s becomes large, then this is not close to 1 over t, clearly. Okay, now let's divide into k stages. We divide combination logic to t over k. Okay, assume that we perfectly divided the combination logic still, again, which is not necessarily true. The bandwidth of k stage version is 1 divided by t divided by k plus s. So sequencing overhead remains the same, basically. That's the key idea over here. You're not getting rid of the sequencing overhead. So as a fraction of your bandwidth, sequencing overhead actually starts increasing. So ideally, let's assume that you divided the pipeline as much as fine-grained as possible. Each stage takes only 1 gate delay. Let's assume that that's the maximum you can go. Now your throughput is limited by s. So in the ideal case, as gate delay becomes 0, your bandwidth is limited by the sequencing overhead. And that's the downside. That's one of the downsides of pipelining, basically. You cannot pipeline arbitrarily small because you will be dominated by your sequencing overhead. And sequencing overhead is really a waste of time. If you remember, we're doing useful work in the combination logic. Sequencing overhead is there just to latch the results so that we can operate on them in the next cycle, right? It's really a waste of time. It's really not useful processing in a sense, right? I mean, it's useful processing, of course. It facilitates you to do the next clock cycle, but it's not useful processing from the perspective of what needs to happen to the instruction, right? Instruction really needs t picoseconds, for example, right? Okay, so keep that in mind. Sequencing overhead is going to be what bottlenecks you in any pipeline. So register delay reduces throughput. Register delay is essentially sequencing overhead between stages. Okay, let's look at cost also, more realistic pipeline cost. So non-pipeline version with combinational cost G, you have G gates in this, but register cost cannot be ignored. So basically the real cost of this is G plus R, where R is the register cost. K-stage pipeline version,
Assume that you perfectly divide the combinational logic again, G over K in each stage. Okay, nice. You don't increase the combinational cost. And that's not exactly true actually in real life, but okay, you don't increase the combinational cost in this case, assume that. But my point here is really register cost increases a lot. I mean, again, this is an approximation, but you multiply it by K. And in fact, you don't multiply it by K, you may actually increase it by a lot more than what we will see, because the intermediate results that you store may be a lot more than what you really need to store as the output of the instruction. So basically your cost increases. Registers increase hardware cost. Okay, so this is an ideal pipeline. Keep this in mind. There are multiple assumptions that I made over here. The assumption is that whenever you divide a pipeline stage into K stages, your combinational delay does not increase. That's not a good assumption necessarily, because you cannot perfectly divide T picoseconds into T divided by K picoseconds and multiply it by K, because combinational logic doesn't work that way, because you need to really divide carefully and latch the results carefully. And this is also not true. G divided by K, you cannot perfectly divide the cost of combinational logic in terms of gates by K. Again, you may need to replicate some resources, as we have seen in the dryer example, and as we will see in the memory example, right? Okay, but keep in mind that there's also other overheads. In addition to increasing combinational overheads, clearly register overheads and sequencing overheads also increase when you increase the number of pipeline stages. Okay, now let's go into pipelining instruction processing. So remember the instruction processing cycle. This is the 6-phase instruction processing cycle. This is another view of it, and we reduced it to 5-phase. Again, there's nothing really fundamental. You can have actually instruction fetch divided into 5 phases itself, right? As we have done actually in the finite state machine for the multi-cycle processor. But this is a good way of thinking about different phases. And remember the single cycle microarchitecture. So as I said, I'm going to build on the single cycle microarchitecture to actually build the pipeline processor. And single cycle microarchitecture looks kind of like this. Okay, and assume that we're doing the ALU operation here. We're not looking at the memory operation. Anyway, it doesn't matter. But assume that you have T picoseconds. Your bandwidth or throughput is 1 over T, approximately. Ignore the sequencing overhead. Keep that in mind, but ignore it for now. Now let's divide this into stages. Okay, let's say instruction fetch, instruction decode, register file read, execute an address calculation, memory access, and write back. And this is my division of combination logic. And somehow I divide and fetch, execute, and memory takes 200 picoseconds, and decode and write back takes 100 picoseconds. It's not a perfect division, as you can see, right? But it's one division that I made. And there's also a register file right over here. So basically, we write to the register file at the end of the pipeline. This ensures that we obey the von Neumann requirement. So von Neumann says, von Neumann model dictates that instructions write to registers and memory at the end, basically. And that's going to happen. Architectural state updates are going to happen at the end of the pipeline. So we're going to get back to this architectural state updates, but we're going to preserve the semantics of the von Neumann model by writing the architectural register file updates, by doing the architectural register file and memory updates at the end. We're going to get back to this. So ignore for now some of the things that need to go back. So these looping things are actually, you need to be very careful about them, right? This is the branch. This is the adder for the branch, right? This is the branch target address calculation. And remember, if the branch target address, if the branch condition holds true, you need to take the target address. So that's basically, this is changing the control flow in the pipeline. So we're going to ignore it for now. Ignore the control flow instructions also because they're going to cause a headache for us. And we're going to deal with that headache later on, because if you have a control flow instruction, you don't know what instruction to fetch next. And ignore that for now. Again, we're going to assume non-control flow instructions. Even if you assume all of these simplicities, I mean, there's also some other thing that we kind of ignored over here, which is the write data. You need to be very careful about that as well. So whenever, basically the key takeaway, one of the key takeaways in this figure is that whenever you have some other later stage communicating a result with a previous stage, as you can see over here with this orange line, or this orange line over here, and there may be other orange lines also here, you need to be very, very careful. Whenever you're updating the program counter, whenever you're updating the registers, you need to be very, very careful so that you get the correct result for instructions that are earlier in the pipeline, as well as you write the correct result into the register file or memory or the program counter. And we're going to deal with that in a little bit. But before we deal with that, we can even ask the question, is this the correct partitioning, right? Before we go into those bigger complications, there's a simpler thing that we can ask. And this is not necessarily a simpler question to answer, but it's a simpler question to ask, perhaps. Did I partition things correctly? Why do I have only 100 picoseconds here? Maybe that's not a good idea, right? Now it's not a balanced pipeline. Your throughput is dictated by the 200 picosecond stages, right? Not the 100 picosecond stages. So to fix that, you try to balance the pipeline. You may try to make the 2 stages over here in execute. You may try to make 2 stages in the instruction memory. You may try to make 2 stages in memory. So now your pipeline becomes longer, right? If you want to divide everything to 100 picoseconds, there are 2 more stages. There are 6 more stages you need to, well, there are 3 more stages you need to add, right? Because you need to divide these 200 picosecond stages into 2, exactly 2. You may not be able to perfectly do that also, which is another question, right? So as you increase the depth of your pipeline to balance the time taken by each pipeline stage, your overhead also increases because increasing the depth of your pipeline doesn't come for free, right? We discussed that you need to add registers and you need to potentially add more resources, and this will complicate the instruction processing also. So keep that in mind. So why not 4 or 6 stages? Why not different boundaries? This is a very, very good question. An ideal pipeline has equal picoseconds in each stage. This is not an ideal pipeline just because I couldn't balance it. Right? You could try to balance it, as I said, but it comes at a cost. Okay, so because of that non-ideality, your throughput is not perfect also. So if you look at this picture, assume that this is 800 picoseconds to really finish an instruction, load word in this case. You take 800 picoseconds for a load word. In a pipeline machine, as you can see over here, you really take, I think, let's see, 200, 200, 200, 600, I guess 800. It's really 1,000. I don't know if this may not be the correct picture. Yeah, you basically take 1,000 picoseconds, right? Because each stage now needs to take 200 picoseconds. Even though this requires only 100 picoseconds, assuming that your clock cycle is 200 picoseconds, we don't divide the pipeline further and add 3 more stages. We have only 5 stages. Then this is supposed to take only 200 picoseconds as well, these 2 stages. As a result, you're wasting some time in each of the stages. So each load word now takes 1,000 picoseconds. So now we've lost the latency. So the latency of each load word actually increased from 800 picoseconds to 1,000. Okay, maybe you don't care about latency of each load word. The throughput increased. So the speed up is still fine, but it's not perfect. So if you perfectly divided this 5 stages into, this 800 picoseconds into 5 stages, your throughput should really increase by 5x, right? You should really be finishing 1 instruction every 5 cycles, every cycle, 5x throughput increase. But no, in this case, we get 4x throughput increase. And you can do the calculation by yourself if you're interested, because the stages are not divided perfectly, basically. And that's the reason. Okay. So let's take a look at how we enable pipeline processing. Basically, we need to add pipeline registers, right? This is the single cycle microarchitecture. If we divide into k stages, as you can see at the bottom over here, this is a single cycle. We're going to divide into k stages, where k equals 5. Basically, we need to add pipeline registers between the stages. So this is the pipeline register between, this is the instruction fetch stage. This is the instruction decode stage. This is the execute and address calculation stage. And this is the memory access stage. And this is the write back stage. And the pipeline registers are named based on the stages that they're getting inputs from and that they're driving. Instruction fetch / instruction ID, instruction decode / execute, execute / memory, memory / write back. So we need to have 4 pipeline registers, as you can see over here. Okay. Meaning that at the end of the stage, all of the results that you need later on should be latched into the registers. True for this stage, true for this stage, true for this stage, etc. Okay. So what are the things? What are some of the things that you need? Well, here you need to have the fetch PC. Here you need to have the instruction register coming out of instruction memory. That's basically the instruction that you have fetched, right? And then you need to probably have the PC +4 because you're going to update the program counter later on at some point. Here you read the data and you basically latch the data that you read from the register file. You actually latch the immediate also, sign extend immediate, and PC +4 still you need it to calculate the target address, for example, and maybe other reasons as well, as we will see later on. Here you latch the result of the ALU, and you actually need the write data for store instructions over here. So you need to propagate everything that you need for later stages. So you can see that this register may be actually quite large, because here you don't have much. You just have the instruction plus PC. But here you decoded the instruction, read the registers, etc. This register can be huge actually, the IDEX register can be huge because it needs to store everything that you need for later stages, right? Later stages including execute, memory, and write back. And you can see that the data coming from memory is the memory data register that's part of the memory write back registers. And the result of the ALU is also latched over here so that you can decide how to write, which one to write it back, depending on the instruction type. So basically, the logic that we have is very, very similar to a single cycle machine. But now we actually need to store the instructions, store the intermediate results. And all intermediate results that are needed for later stages have to be carried in the pipeline registers so that they are provided to the stage that needs that particular data or control input. So I'm not showing control inputs over here. I'm showing data inputs, but control inputs are also similar. Okay. So essentially, if you look over here, no resources used by more than one stage. That's also important. Each stage uses its own resources. They cannot share resources, basically. I mean, this is something that we will discuss later on, also sharing resources potential later on. But in a good pipeline, you should not share resources between different stages. Of course, you can add more ports, but that's to memory, but that's not really sharing resources. That's why you need to have instruction memory separate from data memory over here, because you need the instruction memory for fetching one instruction, and you need the data memory for fetching the data for some other instruction concurrently, right? Okay. So an instruction, all instruction classes must follow the same path and timing through the pipeline stages. So somebody asked, what about write data? Let's take a look at, I'm going to handle that later on, I think. But write data, exactly. So that's, you have a very good point. You need to basically decide what to do with the write data. And we're going to defer that question later on. So basically, you need to decide when to write to data memory. And you should be careful about that also. Okay. And in many pipelines, you actually delay the writing to the last stage. But in this pipeline, it happens to be in this stage. But you need to be careful about how you report the results to the software as well. But we're going to ignore that for now. You have a very good point. We're going to deal with that when we talk about precise exceptions, either in the next lecture or in a later lecture. But very good catch. Okay. So all instruction classes must follow the same path and timing through the pipeline stages. So basically, this is instruction fetch, load word. When the load word is doing instruction decode, it goes through execution, it goes through memory, it goes through write back. So load word actually exercises all of them, right? Remember, load word is the culprit. It's basically exercises all things in a processor, if you will, and it exercises all things in a pipeline. But that's not necessarily true for an add instruction, right? So also remember that. So this, I think, basically you need to be careful with this write data that's coming from load word. So you need to write the correct data from coming from memory. And you need to basically write it to the correct register. So when load word is being executed, so you need to propagate the right register also, ID, so that you use the correct right register ID that belongs to the load word. So basically, whenever you're dealing with an instruction in a particular stage, you need to make sure that you have the correct data signals as well as control signals for that instruction in that stage. So this write register, for example, previously we didn't show this, but it has to be propagated. It has to be propagated through the pipeline as load word goes through the pipeline. And you need to have the right register value here latched, and then use that to index into your register file and write the right data over here into the register file. I assume the earlier question from your fellow student was for this write data, which is updating memory, but hopefully this clarifies this other write data, which is writing from the write back stage into the register file. Writing to the memory is actually a separate issue that we will discuss later on. For now, assume that you're actually writing. Okay, yeah, you meant the other one regarding write back, which is this one basically. Yeah. Okay. But assume that this is fine, basically. Assume that updating memory in this place is fine, but it's not necessarily perfectly fine, as we will potentially see later on. Okay, so let me actually finish a couple of things, and then I'll take a break. But all instruction class must follow the same path and timing through the pipeline stages. Any performance impact? Yes, absolutely. Basically, we're making an add instruction go through the memory access stage, right? So we're wasting time. So load word, fine. But subtract, for example, doesn't need memory access stage, right? But just so that pipeline can operate nicely, we have to ensure that every instruction goes through the same pipeline stage, right? So we're wasting time by ensuring that subtract instruction goes through the memory stage, whereas it really doesn't have to. But fixing this actually takes a lot of effort. So it becomes a not really a fully pipeline processor. If you fix it, it's not perfectly pipelined. So we're going to make sure that all instructions go through every stage. So, but of course, life is not always this beautiful as well. So let's take a look at this operational view before we get into the non-beautiful aspects. Well, it could be beautiful aspects, but there are aspects that you need to deal with, basically. Life is not as nice, meaning that things are not independent. So in this case, I showed you an example of Loadword, and the subtract doesn't depend on the Loadword, right? Okay, so let's take a look at an ideal pipeline. This is the illustration of pipeline operation. This is an operational view. This is time on the x-axis and instruction on the y-axis, if you will. So while instruction in the second time unit, T1, you can see that there are 2 instructions in the pipeline. In the third time unit, there are 3 instructions. The third T3, there are 4 instructions. In T4, there are 5 instructions. At this point, the pipeline is full. Full meaning all of the pipeline stages are occupied. And after that point, we're in a steady state. So I'm giving you some terminology. In the steady state, you're finishing 1 instruction per cycle, basically, assuming there are no dependencies between instructions. And this is called a steady state or a full pipeline. Ideally, you would like to be in this situation, basically. Ideally, you don't want to stall or stop the pipeline. You should always be in the steady state. But we will see that that's not necessarily the case. And this is another view of a full pipeline. Basically, here you see the operational view. You basically look at time on the x-axis again. But now we are going to look at the pipeline stages on the y-axis. And here we're looking at which instructions are in which stage. And at T4, we have a full pipeline, as you can see. And after T4, the pipeline is full, but we're getting new instructions. So for example, we fetched I10. At time T10, we have instructions 6 through 10 in the pipeline. Instructions 0 through 5 are already out of the pipeline because we finished them and written back their results. So a full pipeline is beautiful because you can keep it full like this. Let's talk about the control points in a pipeline before we take a break. Basically, we have the identical set of control points as a single cycle data path, actually. This is easy. So we constructed the control for a single cycle. If you look over here in the pipeline, essentially we have the same control points, right? Memwrite, memread, mem2reg, regwrite, etc. And I'm omitting some things also. PC source muxes over here. There are actually real muxes over here. This is a simpler version of the processor that you have seen. But essentially, the takeaway is control points are the same. But when you exercise the control is different. Meaning, you need to be careful when you set the reg-write signal. So the reg-write signal here should not be set from this register, right? It should really be set whenever the instruction in the write back stage is writing to the register, because that's when we write the write back stage, meaning that you should generate the control signals and propagate them to the register. So the reg-write signal really should be coming from here, right? Similarly to other signals potentially, right? We will see that. Okay, so let's talk about the syllabus. For a given instruction, we have the same control signals as single cycle, but control signals required at different cycles, depending on the stage. Basically, when we assert the control signals are different. And there are 2 options here. One is decode the instruction once using the same logic as single cycle and buffer the signals until they're consumed. And we will see this example in a little bit. So this looks like this, basically. In the instruction decode stage, we have a control logic like before. The orange signals are always the control signals, as we have seen in all of our examples. So you basically decode the instruction, generate the control signals. Some control signals are needed in the execute stage here. Some control signals are needed in the memory stage. Some control signals are needed in the write back stage, but you decode all of them, put them into the register, and then propagate them as long as they're needed. So execute stage signals are used here. Memory stage signals are propagated to the next latch and they're used here. And write back stage signals are propagated multiple latches and they're used here. Clearly, this makes latches or registers, pipeline registers, big, right? Because you generate the control signals over here and you basically propagate them until you know that they don't need to be used anymore, right? They're not required anymore, if you will. This is one approach, and this is the approach that we're going to use in the example later on. But the other approach, this is not the only approach. Like in computer architecture, there are many trade-offs, right? But you don't need to decode the instruction right away fully. You decode partially in each stage. That's the second approach. I don't show the picture here, but carry only the relevant instruction word or field, part of the instruction register in the pipeline, and decode locally within each stage or in a previous stage. So basically decode on demand, let's say, just in time decode, in other words. You don't need the memory signals here, right? Why not decode them here, right? Or just before you need the control signals, decode them. That's the idea. This makes the pipeline registers smaller, but potentially distributes the control logic over different stages. So it could actually be a better option, but it really depends on how you want to design your pipeline. In general, I believe the option 2 is actually a easier to design option so that you can balance the size of your pipeline register. So there's no need for the memory signals over here, for example, or write back signals over here. You carry execute and also the relevant fields of the instruction register. Here you generate the memory signals. So you have the memory, but you don't have the write back and relevant signal. You do have the relevant signals of the instruction register. Here you just have write back at the end. Okay, so which one's better? I already given you the trade-offs. Actually, option 2 is usually better, but conceptually, option 1 is easier to think about. You basically decode the instruction only once, forget about decoding later on, right? But in real systems, it happens as a mixture, basically. Okay, so this is the example of pipeline control signals. So we're going to take a break very soon after this. But basically, if you look at this, you have the control logic decoding the instruction register over here. And then we're propagating the control signals that are needed for write back, memory, and execute over here. And again, they're being propagated. So the signals that are needed in the execute stage are being used in the execute stage, as you can see over here. The signals that are needed for the memory stage get propagated to the memory stage, and they're being used in the memory stage. And the signals that are needed by the write back stage are propagated over there, and they're being used in the write back stage. And again, if you see, remember my example of reg write, you basically carry the reg write signal with the associated instruction until it's really needed, meaning at the write back stage. Same for mem to reg. Basically, you figured out whether this instruction is getting its write data for the register from the memory or the result of the ALU. You basically pick the right one at the right time, meaning at the write back stage. Okay. And then branch is also similar, right? Remember, we said we're going to get back to this. The branch decides which target address should be latched into the PC when it really has the target address. So target address of the branch is available at the end of this ALU result. It gets latched and it gets used. Well, it needs to get propagated somewhere. I don't think it's fully shown here. Actually, unfortunately, the branch target address is not shown here. That should be another input, but the branch control is shown here, as you can see. But basically, the branch decides what is the target address. So there's actually a problem over here that is not shown. So you need to be very careful with the branch signals. Whenever you have a loop, you need to be very careful. Okay, so that was what I showed with the reg write. So we're going to see another example in a little bit, but probably this is a good time to take a break. Now that you know about the data path and the control signals and how they behave. After this, basically, we're going to see the issues that we're going to have with the pipeline with another example, and we're going to try to solve those issues with a real instruction pipeline. Okay, so this is, okay, I have a question over here. I'll handle that before we take a break. Don't we also need to save these instruction parts with registers too? Absolutely. Yeah, this question is saying, so I think this is referring to they carry relevant instruction word field down the pipeline and decode locally within each or in a previous stage. If you decide to choose this option, absolutely, you need to carry the instruction register or relevant, somewhat decoded instruction parts with the pipeline registers, so that you can do the full decoding to generate the control signals for the next stage. Okay, so with that, I think we will take a break. We'll take a 10-minute break. So let's be back at 15:30, and we will cover even more exciting topics.
Okay, I think this is a good time to continue. Oh, let me do this. Don't need that slide anymore. Okay. Okay, so I received another question in the chat. If the branch condition is asserted, what happens to then skipped instructions already being processed in the pipeline? So that's a great question. Basically, if branch is supposed to be taken, and if you already fetch some instructions into the pipeline, what happens to them, right? Depends on which instructions you fetched into the pipeline. If you have not done branch prediction, which we will cover, and fetch the wrong instructions, you need to basically get rid of them. This is called flushing the pipeline. So we're going to talk about that in more detail. So branches or control flow instructions, as I mentioned, we're going to handle them later. But the question arises naturally, right? What happens if you have a control flow instruction that is taken? Then you have a problem, basically. Meaning, if you have a control flow instruction that's not taken, and if you keep fetching instructions sequentially, that's not a problem, right? Basically, you fetch the right instructions and the branch is not going to be taken. But if the branch is taken, meaning that the condition is asserted, then what you fetched is wrong into the pipeline. So you need to get rid of them. This is called flushing the pipeline, or getting rid of the instructions that are fetched wrongly into the pipeline. And we're going to see that. And then we're also going to see how to make sure that that doesn't happen often, which is called branch prediction. Basically, we need to be careful about what to fetch after a branch. And that requires even more hardware, of course. But let's not get ahead of ourselves. That's a great question. And keep that in mind. You have a lot of issues with branches, as we will see. Okay. Of course, we're going to build up to that. But this is another single cycle and pipelined microarchitecture from your book. This is the Harris & Harris example of a simple MIPS microarchitecture that we have seen, single cycle one. And this is a pipeline version of it, as you can see at the bottom. It's actually not a correct pipeline version of it because of this write reg field, as you can see. This write reg field should not be writing to the register at this point in time, right? It should really be writing to the register at this point in time, meaning that going from single cycle to pipeline, you need to be careful as to where you assert the control signals. Even though your data path is very, very similar between single cycle and pipeline processors, when you assert the different control signals and how you should buffer the control signals so that you can assert them at the right places where you're really supposed to assert them is really, really important. That's why pipeline control is extremely important. And essentially what we're going to do, talk a lot about, is going to be pipeline control in the remaining part of this lecture. But basically, I've shown you the bug in this design. If I showed you this picture and asked you the question, what is the bug in this design? You should immediately say this write reg should really not come from execute stage. It should really come from the write back stage, which looks like this. Basically, you need to propagate the destination register ID this way. And also the write read control signal, the write enable signal also should come from the write back stage, basically. And again, this is the correct pipeline data path. And if you pipelining is covered to some detail in the Harris & Harris book, it's not covered at all in the Padham Patel book. So you're left with Harris & Harris, but I'm going to cover some concepts that are not covered in any of the books as well. Okay, so, but they're fundamental concepts. I think the books are not really, as I said at the beginning, books are not really up to date in this field as well as we would like it to be. Okay, this is the example of the pipeline control from the Harris & Harris book for the same pipeline processor that I showed you earlier. We added the pipeline control part of the registers here. We have a control unit. This takes the approach of generating all the control signals as much as possible in the decode stage, as you can see, and then buffering them in the pipeline registers, and then propagating them to the locations, to the stages that they're really needed at. Basically, it's the same control unit. This control unit is essentially the same control unit as a single cycle processor, but the control signals, when they're asserted, are delayed to the proper pipeline stage. Right? You cannot assert the write enable signal, for example, for the register file in this pipeline stage, nor in this stage. You have to assert in this stage, basically. That's the idea. So in that sense, going from single cycle processor to pipeline processor is actually not that difficult. That's why we're building on
single cycle processors and not multi-cycle processors, because multi-cycle processors are, even though they're beautiful conceptually, they basically take the single cycle somewhere else compared to pipeline. And you can think about that a little bit as well. Okay, let's talk about how this instruction pipeline that we're discussing compares to an ideal pipeline. Remember, an ideal pipeline maximizes the throughput with minimal increase in cost. It requires the repetition of identical operations, repetition of independent operations, and uniformly partitionable sub-operations. I've already defined these. I'm not going to go through them again. And we said that fitting examples are automobile assembly line doing laundry. What about the instruction processing cycle? Now we're going to deconstruct the instruction processing cycle as compared to the requirements of an ideal pipeline. And basically, we see that instruction pipeline is not an ideal pipeline. It's a pipeline, but it's not an ideal one. Why? Because we don't have identical operations. Different instructions, not all instructions need the same stages, basically. Not every instruction requires the identical operations, right? It's not like assembling a car. All cars require to go through the same stages in a factory, assuming the cars are the same, right? But in this case, that's not true. As we said, a load instruction requires a memory access stage, and add instruction doesn't. But we're forcing different instructions to go through the same pipeline stages, and that's going to reduce our throughput, as well as increase the latency of some instructions, as we have discussed. This is also called external fragmentation, meaning some pipe stages are idle for some instructions. An add instruction goes through a memory access stage. It does nothing. Nothing meaning, I mean, it has to move through the pipeline, but that stage is not beneficial for the processing of the add instruction. So it's external fragmentation, essentially, from the perspective of the add. Okay, uniform sub-operations, that's also not true. We have different pipeline stages, and they're not the same latency, meaning the real latency to execute what we are supposed to do, the critical path in the combinational logic inside that pipeline stage, is not exactly the same across different pipeline stages. If they are exactly the same, then you have done something really beautiful. But usually, that's not the case. In fact, almost always that's not the case in real designs. You cannot perfectly balance the pipeline stages. You cannot perfectly say, my critical path in each stage is 200 picoseconds, and I cannot do better. Usually, your critical path in one stage is 200 picoseconds, in other stages 150, in other stages 180, in other stage 100 maybe. And in the end, the worst case combinational logic critical path determines your clock cycle time, right? So how do you fix this problem? By trying to balance the pipeline, by breaking the critical path, by having more pipeline stages, of course, right? But it's not an easy problem. So you need to force each stage to be controlled by the same clock in a synchronous design. And this is called internal fragmentation. Some pipe stages are too fast. Their critical path are not as long as the longest critical path, meaning the clock cycle time. That's what dictates the clock cycle time. But all are supposed to take the clock cycle time in a synchronous design. As a result, you're internally wasting some part of your clock cycle in some stages. And again, that's inefficiency, right? That's also increasing your latency of instruction processing. Okay, that's potentially increasing your throughput as well, because you're not balancing your pipeline really well. And finally, independent operations. That's not true also. Basically, instructions are not independent of each other, as we have discussed. You need to detect and resolve inter-instruction dependencies to ensure the pipeline provides correct results. Now, that's not always true, of course, right? There could be a sequence of code where all instructions are independent of each other, and that's great. In that case, the pipeline is perfectly full. But this is not always the case. And in some workloads, in some applications, there are serious dependencies, right? For example, if you look at pointer-based applications, pointer chasing, memory accesses depend on address calculations done by add instructions, and then the previous memory accesses dictate what the next memory accesses will be. So a lot of things are dependent on each other, right? And in the presence of this, you still need to provide correct results, right? And this will lead to pipeline stalls, meaning pipeline is not always moving. Pipeline will have to stall sometimes such that the result that's needed by an instruction is produced by an earlier instruction that's in the pipeline. And we're going to see that this is important. And then there's also control flow that is mentioned by one of your colleagues, right? What if you have a branch control flow that's changing the flow of control? You need to deal with that. You may need to flush the pipeline once in a while, or part of the pipeline, as we will see. Okay, so basically issues in pipeline design boil down to multiple things. And these are very specific to instruction pipelines. You need to balance the work in pipeline stages as much as possible. You need to find out how many stages. You basically need to, as a designer, you need to decide how many stages you have and what is done in each stage, so that you maximize throughput, minimize the sequencing overhead, get a good cost design point, so there get a good latency. So basically, there are a lot of concerns over here, and people have tried to do it perfectly, but there is no perfect way of doing this because it's not an easy task. You need to keep the pipeline correct, moving, and full in the presence of events that disrupt the pipeline flow. And this is going to be our subject in the next few lectures, basically. How do we keep the pipeline correct, moving, and full? Meaning you need to handle the dependencies, data dependencies between instructions, as well as control dependencies like we have discussed. You have a branch, you need to change the control flow. What do you do? On top of this, you need to handle resource contention. Resource contention in a resource also affects the correctness, whether your pipeline is moving and whether your pipeline is kept full. And we're going to talk about that next. And also handling of long latency multi-cycle operations. So these three things affect whether or not you can keep the pipeline correct, moving, and full. Of course, correctness, you should really provide that correctness. But whether or not you can move the pipeline and keep it full depends on how you handle these things. So long latency multi-cycle operations are usually a culprit. So if your memory access takes 100 cycles, does your pipeline stall for 100 cycles, right? What do you do in that case? And that's going to always cause problems for us. These long memory accesses, unfortunately, are going to cause problems for us in all of our designs, and we're going to develop methods to handle them. Handling exceptions or interrupts, we're going to talk about them. Basically, what if an instruction is faulted? You divide by 0, for example. How do you handle that? What if there's an external interrupt? You have an input coming from the user, and you have some instructions in the pipeline. How do you handle that? How do you make sure the von Neumann model does not break, basically? And finally, advanced is improving pipeline throughput. How do we minimize the stalls in a pipeline? And we're going to talk a lot about that as well. Okay, so this slide is very important, actually. These are the key issues in pipeline design. And we're going to talk about the last three. We kind of talked about balancing work in different pipeline stages, but we're not going to talk more about that going forward. But keep that in mind, that balancing work in pipeline stages is really important. So let's talk about cause of pipeline stalls. So what is a stall, first of all? A stall is a condition when the pipeline stops moving, basically. And there are three major reasons for it. One is resource contention. Second is dependencies between instructions, data and control dependencies. Control dependencies are caused by control flow instructions that write to the program counter. And the third one is long latency or multi-cycle operations like memory operations, for example. But long latency divisions and adds could be also. Basically, these are also called dependencies. I use dependencies. I try to use dependencies in general, but dependencies is also fine. Less desirably, they're called hazards. I don't know why, but your book and some other books like calling these hazards. That's not like a health hazard. I mean, clearly you need to handle them to make sure things are correct, but it's not like the COVID virus that we're dealing with right now, right? It's not immediately attacking us. So you need to deal with it nicely so that they don't become a hazard. So I like the dependency because dependencies are really the fundamental cause of why you need to stop moving the pipeline for some reason. And how you can get around that is going to be our task in the rest of this lecture, for example. So dependencies dictate ordering requirements between instructions. And this is really, really important. And we're going to see different types of dependencies. Some dependencies are very, very fundamental because an instruction needs the result of another, right? That instruction requires that result. As a result, you need to make sure that that instruction gets the correct result. So there are two types, clearly, data dependence and control dependence, and we will see both. Resource contention is sometimes also called resource dependence. And while the terminology is correct, I think, I don't want to call it resource dependence, I call it resource contention, because it's not the same thing as an ordering requirement between two different instructions. It's really the fact that you don't have enough of a resource and multiple things are contending for it. Basically, resource contention is really not fundamental to program semantics or dictated by program semantics, so we're going to treat it separately. Okay, so let's talk about resource contention and get it out of the way for now. We actually talked about the resource contention, right? We talked about an example of the dryer to restore the throughput. We need 2 dryers to restore the throughput, or a faster, more expensive dryer, right? But resource contention happens when instructions in 2 pipeline stages need the same resource, just like with the dryer we saw. In that case, 2 different instructions need the dryer. So we actually wanted them. So the solution 1 is eliminate the cause of contention, duplicate the resource, or increase its throughput, just like we did with the dryer. We can, for example, use separate instruction data memories, which we have done. We're going to see the concept of caches. Caches are essentially memories. Or you can use multiple ports for memory structures. And we've already, we also kind of do it as well with the register files, but we don't talk about that, right? We have 2 read ports and 1 write port to the register file. Well, we did talk about that a long time ago, but we don't talk about it anymore. Okay, the second solution is detect the resource contention and solve one of the contending stages. If you don't want to do solution 1, because it's too expensive for some reason, you don't want to duplicate huge memory, for example, then you need to somehow detect that 2 stages are trying to access the same resource and you cannot handle both stages requests at the same time, and stall one of the contending stages. So which stage do you stall becomes important. And the answer is easy over here. For example, what if you had a single read port and a write port for the register file, and one instruction needs to write to the register file and the other instruction needs to read from the register file, but you cannot handle both of them because a single port that handles both reads and writes. Then I think you need to actually write to the register file first, because that's the older instruction, right? That happens later in the pipeline stage. If you don't prioritize that instruction will not go away from the pipeline. And as a result, your pipeline will have to stall at some point. So basically, solution 2 requires prioritizing the stages that are later in the pipeline that belong to older instructions in program order, so that you can get those instructions out of the pipeline quickly and keep moving the pipeline. So remember, our key goal is keeping the pipeline correct, moving, and full as much as possible. Okay, so you need to handle the resource contention with that in mind. Okay, so let's take a look at an example of resource dependence register file. If you look at this picture, we're going to see a sequence of this sort of pictures. So here, add instructions writing to register S0, and end instructions reading from register S0. And we actually have a problem here, right? For example, this add instructions writing to register S0 in 5, stage 5, pipeline is cycle 5. But this add instruction is already in the pipeline and trying to read it in cycle 3. First of all, you need to handle this problem. And we're going to talk about that. Assuming that you handle that problem and make sure that this AND instruction is reading the register file in cycle 5. And we're going to see how to do that. So as you can see, OR instruction is also reading register S0, and sub instruction is also reading register S0. So until register S0 is written into the register file, these instructions cannot proceed. And that's the problem with dependencies, as you can see. So this picture is wrong, meaning this AND instruction cannot read the register file at stage 3, cannot read it in stage 4, because the result that it needs, S0, is not in register file yet. It can possibly read the result in cycle 5 over here, meaning it should stall until then. It should do the register file read over here, assuming that the resource contention is handled well. Okay, and what does that mean? So basically, we're going to assume in the later parts of this lecture and the next lecture, the register file can be read and written in the same cycle. So an instruction that's writing to the register file, it can write in the first half, and the instruction can read that's reading the register file can write in the second half. Of course, this picture is wrong, but assuming that this AND instruction is reading the register file in cycle 5, this assumption enables us to have the add write destination register S0 in cycle 5, and the AND to read the destination source register S0 in cycle 5, because we are assuming register file can be read and written in the same cycle. So this is an assumption. If this assumption is not correct, then this AND needs to wait and read the register file over here, actually. Okay, so okay, but we're going to do this. It makes this assumption, and your book makes this assumption also. Write takes place during the first half of the cycle. In this case, read takes place during the second half of the cycle. Assuming that you can afford that, no problem, right? Of course, you should be able to afford that. However, operations that involve the register file have only half a clock cycle to complete the operation right now, right? So that's the downside of this assumption. So it's not always a great assumption. We're going to make it. We're going to use it as a simplifying assumption, basically. So one of your colleagues asked a great question. Can't you already take the result after it went through the ALU? Basically, the question is this. The add instruction already produced its result after the ALU, right? S0, basically the result is available. Can't you take that result? And the answer is yes. But we need to provide some more hardware to be able to do that. And that's called data bypassing, data forwarding. So we're getting ahead of ourselves. I'm going to talk about that. And but we need to provide enough hardware more hardware to be able to do that. So it's called bypassing. Basically, you don't read the result from the register file, but you read it from the output of the ALU. And that way, you don't need to stall this AND instruction. And that's a great observation, basically. Okay, so we're going to get to that. So let's talk about data dependencies before we talk about that. Basically, there are three types of data dependencies, and one is real. The other two are, I don't want to call them unreal, but they're there because we don't have enough names for registers, as we will see. The real one is really called a true data dependence, flow dependence. It's really a data flow dependence from the data flow sense. Basically, an instruction requires the result of another instruction. It's called a read after write dependence. There's also output dependence, write after write dependence. If two instructions are writing to the same register, you could eliminate that by writing to different registers. So this dependence goes away if you can do that. Anti-dependence is if one instruction is reading from a register that a later instruction is writing to. This is clearly not a dependence, but you should be careful about how you handle this. Because if you do the wrong ordering of instructions, you may actually have a problem. So basically, which ones cause stalls in a pipeline machine? For all of them, you need to ensure semantics of the program is correct, basically. You will see a pictorial view of this dependence in the next slide, actually. But for all of them, you need to be careful. But the real dependence is the flow dependence, as you will see. So flow dependencies always have to be obeyed because that they constitute our true dependence on a value. An instruction really needs the result of another instruction. Anti and output dependencies exist due to limited number of architectural registers. You cannot encode. You don't have enough architectural registers, basically. Remember, in MIPS, we have 32. In x86, we have 16. But different architectures have different number. In LC3, we have 8, for example. If you cannot have enough architectural registers, you need to use the names of the architectural registers. And they happen. Essentially, there depends on a name, not a value. And we're going to fix that in out-of-order execution by doing what's called renaming later on. We will later see what we can do about that. But let's take a look at a pictorial example. These are the data dependence types. So this is the first instruction. It's writing to register 3. It doesn't matter what it's operating on. But the second instruction is reading from register 3. Clearly, the data value that the second instruction needs, sequential instruction needs, is written by the earlier instruction. It's a read after write dependence. This instruction, reading after write happens. So this is a true dependence you cannot eliminate. Anti-dependence. This instruction is earlier instruction is reading from register 1. The later instruction is writing to register 1, right after read. This is not a true dependence, clearly. This happens because you don't have enough registers. The compiler happened to encode the result of the second instruction into register 1. If you had thousands of registers, let's say, this could have been register 1000. Because this register 1, the value in this register 1 has nothing to do with the value in this register 1. They just happen to go to the same register because you don't have enough registers, right? But you should still be careful that you don't write into register 1 the result of this instruction before the earlier instruction reads it, right? So you need to pipeline carefully, but this is trivial in a pipeline that I showed you earlier. If you always write the result at the end of the pipeline in sequential order, you don't have a problem with these anti-dependencies. Similarly, with output dependencies, you don't have that problem. Also, if you look at the output dependence, earlier instruction is writing to a register, and later instruction is writing to the same register. Again, these have nothing to do with each other, right? There's no true data flow between the instructions. This exists because you don't have enough register names. This could have been register 1000 or register 55 if this was available, right? It is not available. That's why this is register 3. Again, you need to make sure that these writes happen in program order to preserve the von Neumann model semantics. And as long as you write to the registers at the end of the pipeline stage, right before that instruction gets out of the machine, in sequential order, you don't have a problem with anti and output dependencies. But flow dependencies are real, and you need to solve them. And they will cause problems, as we will see, as we have already seen, actually. Okay, so let's take a look at the pipeline operation example. So Loadword, subtract. Subtract does not depend on Loadword, so life is beautiful. But what if the sub were dependent on Loadword? And that brings us to data dependence handling. And this is actually not an easy case. Loadword is special because you cannot do the trick your colleague suggested with Loadword, because Loadword actually provides its data, has its data at the end of the memory stage. But subtract actually needs the data right here, right? So you cannot take the output of this and put it over here easily, as we will see. Okay, We will see. If this is not clear, we will see it in a little bit. Okay, so basically, what if sub were depend on LW? And that brings us to data dependence handling. So I have some more readings for the next few lectures, and clearly pipeline processors that I mentioned over here. But in the next few lectures, not just pipeline processors, but when we talk about out-of-order execution, this is a great reading that talks about the microarchitecture of superscalar out-of-order processors. I don't like the title. It should be really superscalar out-of-order process. We're going to see all of the concepts covered in this paper. There's also H&H chapter 7.9 also covers them. But this also has nice definitions of this dependencies and how to handle them as well. But it doesn't go into as much detail, as many concepts as we will cover. It goes into a lot more detail in some other concepts that is not necessary, but we will cover more broad concepts in this particular slide quickly. So basically, as I said, anti and output dependencies are easy to handle. Right to the destination only in the last stage and in program order. Flow dependencies are more interesting. So we're going to focus a lot on flow dependencies. And there are 5 fundamental ways of handling flow dependencies. I mean, they implicitly somewhat handle the anti-dependencies also potentially, but that's not important. And we're going to see these. So one of them detects and waits until the value is available in the register file. This is slow. One of the second approach detects and forwards and bypasses the data to the dependent instruction, what your colleague mentioned. The third one detects and eliminates the dependence at the software level by reordering in the instructions such that you don't get into these situations where you need to actually detect even in hardware the dependencies. The software somehow reorders the instructions, add no ops, for example, so that you don't run into this dependency problem in the pipeline. So these all require detection. The fourth one over here predicts the needed values and executes speculatively and verify. This is called value prediction. We're going to look at that. And the last one over here does something else. Basically, there's no need to detect. Basically, it switches to some other thread that is completely independent. And we're going to see that also because these are all very powerful. In fact, GPUs do that, for example, in their pipelines. They basically don't have data dependence detection hardware because they switch to some other thread every cycle. And that's called fine-grained multi-threading. But let's not go into that right now. Let's talk about how to detect these dependencies because they all require detection. And some of them require detection at the software level. Software meaning compiler, but could be the programmer also. Okay, remember these are dependencies, flow, anti, and output. And we're going to care a lot about flow dependencies. So let's take a look at these flow dependencies in the pipeline. So in this case, we have add-I instruction writing to RA, and we have a bunch of add-I instructions reading from RA. The second input doesn't matter, as you can see. So basically, this add-I instruction writes to the register file in the write back stage, right? This add-I requires its operands in the decode stage, but it cannot get it. It cannot get RA because the RA value is not available, so it has to wait. True for this RA, true for this add-I, true for this add-I. Basically, until this instruction writes to the register file, no other instruction that reads the destination register can proceed. So only here we can proceed the other instructions. Okay, let's take a look at it in a more formal way. So an instruction is writing to Rx, another instruction is reading from Rx. What should the minimum distance be between these instructions in this pipeline such that you get the correct value into the input of the second instruction J? And if you do this calculation, if this instruction is writing to here, this instruction cannot read it at this moment because the value is available over here, right, at the end of the write back stage. So basically, you need to make sure the dependent instruction is delayed 3 more cycles before it can be decoded, because the value written by this instruction is in the register file at the end of the cycle. Now this instruction can read the register file, assuming the register file write and read are not done as we discussed earlier in half a cycle. So 3 bubbles. This is called pipeline bubbles. Basically, you need to stall the pipeline for 3 cycles to ensure that this data dependency is obeyed, right? Of course, with what I showed you earlier, if this instruction can write to the register file in half of the cycle and this instruction can read from the register file in half of the cycle, you can move this to 2 bubbles only. That's the beauty of doing that half cycle read, half cycle write. But essentially, the distance between them have to be 4 over here, which leads to 3 bubbles. Sounds like a bad idea, right? You're really destroying the throughput of your pipeline if you do this. So essentially, what is a stall? Stall makes the dependent instruction wait until its source data value is available in the register file. To be able to do that, you need to stop all upstream stages and to drain all downstream stages. Downstream stages mean stage instructions that are already in the pipeline need to go, continue so that they can write to the register file, etc. But instructions that are just at the beginning of the pipeline that are dependent and beyond need to stay. You need to wait, basically. That's called stalling. And there are multiple approaches to stalling. So I'm going to cover this. Basically, interlocking is one way. Detection of dependence between instructions in a pipeline processor to guarantee correct execution. So that's the idea of interlocking. This is also called interlocking, stalling. How do you detect this dependence? And there are multiple ways of doing this, software-based interlocking versus hardware-based interlocking. And we're going to talk about both, actually. Software can do this if it knows the pipeline structure. So basically, if you look at this picture, if the software knows the pipeline structure, it says, okay, I have an instruction writing to Rx. I have another instruction reading from Rx. I certainly cannot put these instructions. They have to be apart from each other by at least 3 instructions. So what I'm going to do is I'm going to reorder my instructions such that independent instructions fit in these bubbles. And if you cannot do that at the software level, the software can say, okay, I'm going to add no ops, no operations into these bubbles, such that the hardware doesn't need to do dependence checking. Okay. So this is the beauty of software, right? If you in the software, if you know the pipeline structure exactly, you can compile your code, or as a programmer, you can reorder your code such that independent instructions go into these bubbles, or no operations, no op instructions go into these bubbles, such that the hardware doesn't need to do the dependence checking. That's the idea of software-based interlocking. Software knows the pipeline structure and schedules instructions or inserts no ops, such that you don't run into these dependence problems in the pipeline. Now, if you insert no ops, you waste resources, right? Clearly, that's not a good thing. But if you can schedule the instructions in some order such that you can make use of these cycles that should be bubbles otherwise, that's great. Hardware-based interlocking is clearly what I will show you in a little bit. Basically, hardware detects these dependencies and does the stall or does other things. And in fact, MIPS acronym is very, very interesting here. MIPS is an ISA that was designed with the philosophy that hardware should be as simple as possible. It should not do data dependence detection. It should be pipelined, but it should, the data dependence detection should not be done by the hardware. And the acronym actually stands for that. It stands for a microprocessor without interlocking pipeline stages. Meaning hardware doesn't do interlocking, software does interlocking. And in fact, this philosophy of MIPS made a lot of advancements, created a lot of advancements in compilers, where the compilers actually did scheduling of the code to manage the pipeline nicely. We're going to get back to that later on also. But today, actually, it's a combination of both, basically. You need to do both software and hardware-based scheduling of instructions, as we will see later on, to achieve the maximum performance. But keep in mind that software can actually play a role. And MIPS was actually designed such that software does most of the heavy lifting so that you can handle the data dependencies. Okay, let me finish the approaches to data dependence detection, and then we're going to conclude this lecture, and we're going to continue pipelining in the last lecture. But one approach is scoreboarding. The idea is very simple. That's why I'm going to finish it. Each register in the register file has a valid bit associated with it. An instruction in the decode stage, when it's supposed to write to the register file, sets the valid bit when it's being decoded, or reset the valid bit. Valid bit becomes 0, saying that I'm going to write to the register file later in the pipeline. Okay. Or this particular register later in the pipeline. And another instruction that later comes to the decode state checks if all its source and destination registers are valid. Now, if that's the case, then it can continue. It can read the register file, right? No problem, because nobody's going to write to that register. Nobody said, I'm going to write to that register, wait for me until I write to the register. That valid bit is really a synchronization bit between the instructions. It basically specifies whether the register has the correct value given the instructions in the pipeline. And if the register doesn't have the correct value, it's invalid because somebody is going to write to it, okay? And whenever you're decoding an instruction, you can basically simply check these valid bits. And if you don't have a source or destination register valid, you basically stall the instruction. If the instruction has its sources and destination valid, there's no need to stall, there's no need dependence because you know that. Otherwise, you stall the instruction because there is some dependence. And the advantage is very simple. This is 1 bit per register that's basically in the decode stage. Of course, whenever you're writing to the register in the write back stage, you update the valid bits, right? Okay, and you need to be careful about how to update the valid bits also, which we're not going to get into right now. But disadvantage is you need to stall for all types of dependencies, not only for flow dependencies, actually. In fact, you can actually fix this problem such that you don't stall for all types of dependencies, but you actually stall for only flow dependencies. But that makes the scoreboarding a little bit more complicated. I'm not going to go through that, but you can think about that. The second approach to dependence detection, hardware dependence detection, is combinational dependence check logic. Basically, you have a special logic that checks if any instruction in later pipeline stage is supposed to write to any source register of the instruction that is being decoded. And it's beautiful. It's very simple, right? You know that an instruction in the write back stage is going to write to register 5. In the decode stage, you check whether you're reading from register 5. You know that an instruction in memory stage is supposed to write to register 3. If you're reading from register 3, you check whether these two match. And if they match, you stall, basically. So basically, it's a combinational matching logic. It matches the register IDs of the instructions that are supposed to write in later stages to the register that we are supposed to be reading. If yes, we stall the instruction and the pipeline. If no, there's no need to stall because there's no flow dependence. The advantage of this is there's no need to stall on anti and output dependencies. So we stall only on flow dependence in this case, which is great, right? Because you don't need to check the anti and output dependence in this case. You just check whether you really need to value of an instruction that's writing to the register that you're supposed to read from. Remember, we handle anti and output dependencies by writing to registers at the end of the pipeline, okay? So there's no really need to stall for them. But scoreboarding doesn't allow us to do that. But if you have this combinational dependence check logic, you're just checking for data flow dependencies. The disadvantage, logic is more complex than a scoreboard because you need to do this checking. And basically, you need to check at the decode stage, you need to check if any of the source registers that you're trying to read from matches any of the later registers that are going to be written by any of the instructions in later stages in the pipeline. So if there are 1,000 stages in the pipeline, I'm exaggerating, of course, you have 1,000 possible writing instructions to those registers. And if each instruction is writing to one register, you have 1,000 things to check. If you have 3 stages, you have 3 things to check. And you have to do this for all source registers, right? So basically, logic becomes more complicated as the pipeline becomes deeper. You have more pipeline stages, and it becomes wider, as we will see, meaning we have more instructions in a given pipeline stage. Don't worry about that right now, but we will actually make the pipeline deeper and wider as we go along in this course. But we're going to see this logic in the next lecture very soon. So once you detect the dependence in hardware, what do you do afterwards is another question, basically. So let me actually quickly give you the ideas, and we're going to see the implementation in the next lecture. But basically, the observation is that dependence between 2 instructions is detected before the communicated data value becomes available. And you need to do that. You have to do that, actually. So there are multiple options you have. One is you can stall the dependent instruction right away. You can say, oh, I'm going to wait until the instruction that is going to write to the register file writes to the register file. I'm going to stall and wait. This may be low performance, as we will see. The second option is you stall the dependent instruction only when it's really necessary. Basically, you try to forward the data or bypass the data as early as possible. As your colleague mentioned, the results available in the ALU, give the result back to the register file stage so that the instruction that's waiting for that result can continue as soon as possible. Don't wait until the result gets written to the register file, right? We have all these stages that the instruction needs to go through so that it needs to write to the register file. Don't wait because the result is available. Just bypass it or forward it to the stage that's reading the result, that's reading the register file. And there could be multiple other options that, as we will see, but I'm not going to talk about them. So basically, that's the idea of data forwarding and bypassing. I'm going to give you the idea, and then we're going to finish up over here. Basically, we already discussed this actually because of the question that came during the lecture. Essentially, a consumer or dependent instruction has to wait in the decode stage until the producer instruction writes its value into the register file, if you take option 1, if you don't do forwarding or bypassing. And that's a problem. So goal is we do not want to stall the pipeline unnecessarily. Remember, we want to move the pipeline, keep it full, and keep it correct all the time. If you want to do that, this observation is very helpful. The data value needed by the consumer instruction can be supplied directly from a later stage in the pipeline instead of only from the register file. Whenever the data value is available, supply it to wherever the instruction needs it. But of course, this comes at a cost. And the idea in data forwarding and bypassing is to add additional dependence check logic and data forwarding paths, meaning wires and buses, and muxes also, multiplexers, as we will see, to supply the producer's value to the consumer right after the value is available. Okay? And we've already seen an example. The benefit is consumer can move in the pipeline until the point the value can be supplied. There's less stalling that happens. You don't need to wait until the value is written in the register file. You can get the value from the ALU result in the next stage. That way you don't need to stall. And this actually brings us to closer to the data flow operation principles, because we're really flowing the data as soon as it's available to the dependent instruction. Okay, so that brings me to the end of this lecture. This is a great place to stop, actually. We're going to pick up from these data dependence concepts, and we're going to talk about implementation of how we actually do it, and we're going to go into more detail. But I actually hid a couple of slides over here. This was I would recommend you actually take a look at slides 63 and 64 also. We're going to talk about control dependencies later. But given that one of you asked the question, what about control dependencies, right? What about branches? This is really a special case of data dependence as well. It's really data depends on the instruction pointer or program counter. And we're going to actually talk about that separately after we handle the data dependence handling in the next lecture. Okay, are there any burning questions? I think we handled a lot of good questions in the lecture. So if there are any other burning questions, I'm happy to handle them. Let me check the chat. I don't see any questions over here. Otherwise, in the next lecture, we're going to start with more implementation and some other concepts on how to actually handle data dependencies nicely. Okay, until then, take care. Have a good weekend. And okay, there's one question that I will handle. I think it's a direct message to me. In scoreboarding, you said an instruction that is writing to the register resets the valid bit. Doesn't that just concern the flow dependence at the moment? That is true. Yes, that is true. Not necessarily though, because whenever you write to a register, you set the valid bit. And an instruction. So if you see over here what I said, an instruction in the decode state checks if all its source and destination registers are valid. In this case, I'm also looking at write after write and write after read dependencies. And the reason is to keep the logic simple. And you can think about that on your own. But basically, the way I describe scoreboarding over here, if there's a write after write dependence, for example, if an instruction in a later stage is writing to register 3, and another instruction here is writing to register 3 also in the decode stage, the instruction that's writing to register 3 cannot proceed until the later instruction, earlier instruction in the pipeline writes to register 3. And that's a write after write dependence, right? And the reason I actually made it this way is so that I can keep the scoreboarding logic simple. Of course, you can eliminate that. You can basically somehow make sure that an instruction in the decode state doesn't check if the destination register is valid. But you need to be careful after that point, right? Because now you may have multiple instructions in the later stages writing to the same destination register because of write after write dependencies. And you need to make sure that the instructions that are reading from them gets the correct value. And basically, there are some complications here. But you can make it work also, essentially. So that's a good question. That's a subtlety. Scoreboarding can enable you to stall only for write after or read after write dependencies, true flow dependencies, but not in the way I described it over here. And you need to be a little bit more careful if you want to stall only for read after write dependencies. Okay, I don't see any more questions. So at this point, I think have a good weekend, and I will see you next Thursday, where we will cover very interesting topics of handling data dependencies more. Take care.